Hi everyone, welcome to CS 188, Section 8, and today we're going to be talking about sampling and VPI, value of perfect information. So first, let's start off with sampling. So let's consider a BaseNet, such as the one we have on the right, where cloudy and then rain, and then the rain depends on cloudy. So in general, if we want to answer questions, queries such as the probability of some query variables Q given some evidence variables E. In the past, what we've done is we've run variable elimination. And this is an exact way of calculating these queries, probability of Q given E. But sometimes this can be expensive. If we have a really large BaseNet, then we have to do a lot of work when we do variable elimination, a lot of joins and a lot of eliminates. So to make this faster, we want to do approximate inference. And how are we going to do that? Well, that's going to be sampling. So the basic idea is that we draw n samples from the distribution, and the distribution can be represented by a BaseNet. And from these samples, we can compute an estimate of the posterior, which is what we're looking for, which is probability of the query variables given the evidence variables. So now we're going to talk about different ways of doing this, and all in the context of the BaseNet that we have here. So as our running example, let's say that we want to compute the probability of that it's cloudy plus C given plus R. So now let's say we draw a bunch of samples. We'll say we draw 4 samples. So when we're sampling our BaseNet, we get plus C plus R, maybe we get plus C minus R, we get plus C plus R, and maybe we get minus C minus R. So we're going to start off with the most basic approach, which is called prior sampling. So in prior sampling, what we do is we ignore the evidence, and we sample from the joint. So that's what I did over here. I just looked at my BaseNet and I sampled different values for cloudy and different values for rain. Then what I do is I perform inference by counting the right samples. So since I want to compute the probability of plus C given plus R, what I do is I only look at samples that have a plus R. So that's this one and this one. I'm actually going to add another just to make everything a little nicer. And let's say I also have that. So this is also plus R. And I see how many of them are plus C. Well, 2 of them are out of a total of 3 because there's 3 arrows. So that's prior sampling. But now we notice that we actually, when we were computing probability of plus C given plus R, we ignored 2 samples. So it seems like we did some wasted work. So this is where rejection sampling comes in, which is another algorithm. That's a modification of prior sampling. So what happens is that while you're sampling, you reject a sample if it's not consistent with the evidence. And then all you have to do is do inference by counting samples. So let's look at the samples I drew above. So I'm trying to compute the probability of plus C given plus R. And let's say, okay, so I go here, so I'll do this in blue, and okay, so plus C given plus R, so this matches my evidence, so it's all good. Now I go here, so I start to sample plus C, and then I sample minus R, and this is not consistent with my evidence, because I assume plus R, so then I would ignore that sample. Now, this one is sorry? Now this one is consistent because it has a plus R. This sample is not consistent because it's minus R, and this one is consistent. So we would only keep the samples in blue. Now, when we do the calculation, we get the same exact thing. Probability of plus C given plus R. And again, we do counting, and we get 2 on top and 3 on the bottom. So now you might ask, well, how did this save us any information or any work? Well, imagine that you have a really long single chain Bayes net. And let's say your evidence is the very top node. If you do prior sampling and it's not consistent with the evidence, then you're going to sample all of these nodes, and then you're actually just going to ignore it. So this chain is super long, and I'm doing all this work even though I didn't match this one. So that's where you get the gains using rejection sampling and why it's faster. Okay, so next we're going to look at a different method, and this is called likelihood weighting. So in the previous approaches, the issue was the evidence. We were doing wasted work. So what likelihood weighting does is you actually fix the evidence. And then once the evidence is fixed, you need to account for this because, well, I'll go into this in more detail. Then next, what you do is you weight each sample by the probability of the evidence given the parents. So in an equation form, it'll look something like this. Each one will have a weight W, that is the product of all evidence variables E of the probability of that variable given the parents of E. Then lastly, what you do is you do inference by counting using the weights. Okay, so now let's go through this example over here on the right. So what happens is, first let me get rid of the So what's going to happen is I'm trying to compute probability of plus C given plus R. So first, I fix plus R. I fix my evidence. So let's say I'm going to draw 4 samples. Now, I'm going to draw samples of cloudy. So let's say I get a plus C, maybe I get a plus C, I get a minus C, maybe I get a plus C. Now what I do is I assign a weight to each. So the weight of the first one is the probability of the evidence given its parents. So probability plus R given plus C is 0.8. This will, same thing. this right here is probability of plus r given minus c, 0.1, and this is 0.8. Now, if I want to do probability plus c given plus r, do the same thing as counting, but I use the weights. So I get 0.8 plus 0.8 plus 0.8 over all of them, the sum of all the weights. 0.8 plus 0.8 plus 0.1. And that's it for likelihood weighting. So now you might ask, why are we doing this weighting? Well, because we're fixing the evidence, so we're fixing these r's right here. We're not actually sampling them. We're introducing a bias into our sampling procedure. So the weights serve to counter this bias. Okay, so now we're going to move on to the next topic, which is the value of perfect information. So let's consider a scenario where we have an unknown variable, the weather, and we also have an unknown variable, the forecast, because the forecast depends on the weather. Let's also say that you have an option, you have an action that you can take, and the action is whether you bring an umbrella. And you get some utility, which we denote here as U, that depends on the weather and whether you bring an umbrella. So you can imagine if it's raining and you bring an umbrella, you get a high utility. If it's not raining and you don't bring an umbrella, you get a high utility. Otherwise, you might get a lower utility. So the first question that we want to ask is, what is the expected utility of an action? How good is bringing an umbrella? So we'll say that the expected utility, EU, of, let's say, umbrella equals take, is the utility of the weather and of taking the umbrella. However, we actually don't know the weather. It's a chance variable. It's an unknown. So what we need to do is we need to do the expected value. So we sum over all possible weather and we weight by the probability of W. So now that we know that an expected utility for an action, what you might want to know next is, what is the maximum expected utility? So what's the best action I can do? So it's relatively simple. It's the max over all actions of the expected utility of that action. In this case, the umbrella. So, and then for the umbrella, I either take it or leave it. So this max is over two different actions, take or leave. So now that we have maximum expected utility defined, we can talk about VPI, which is the value of perfect information. So on a high level, it's what's the value of knowing a chance variable. So it's as if someone came up to you and they said, how much money would you pay to know what the forecast is? That's what VPI is trying to answer. So first, let me write down the equation for VPI. So the value of perfect information of finding out what the variable E prime is, given what you already know E, is you consider all values that E prime can take on, the likelihood that E prime takes on that value, given your evidence, times the maximum expected utility of your new knowledge, E prime, and your old knowledge. And the improvement, so you must subtract out the maximum expected utility if you only just knew E. So this is how much information you gained. So one question you might ask is VPI ever less than 0? Well, let's think about this. So is the VPI, can it be greater than 0? Well, if the new variable E prime tells you exactly what the chance variables are, then you can only do better. So that's good. Can the VPI be 0? Well, if the new variable is totally unrelated, let's say I'm trying to predict which I bring my umbrella or not, and someone tells me, oh, this team won a baseball game. That has nothing to do with it. So the value of finding out that the baseball team won tells me no information, so I get 0. That's good. Now, can my VPI be less than 0? So this means that giving me more information decreases my expected utility. And this just doesn't make sense, because getting more information should never hurt you.